Hello and welcome to another deep dive. Today we're going deep into the world of industrial control systems and their cybersecurity. You've given us a really fascinating collection of material focusing on how to monitor and secure these really vital systems alongside a paper that really digs into the vulnerabilities that can be found within PLC software and another one that's like a complete guide to PLC cybersecurity. Our mission today is to pull out those crucial insights from these resources to give you a solid understanding of what ICS cybersecurity really looks like. We'll be looking at everything from, the architecture to potential threats and even proactive defense strategies. So let's dive in.
Yeah, one of the things that really struck me going through this material is how the traditional separation between IT and OT is starting to blur.
Right.
That classic division between information technology, your typical computer networks, and operational technology, the specialized systems controlling physical processes in industrial environments, well, it's not as clear-cut anymore.
It's definitely changing.
Definitely. And this IT-OT convergence, it's a big deal because it means we're seeing more and more OT assets popping up in the IT space. They're appearing on IT networks for things like remote access, data sharing, and monitoring.
Yeah, and, it used to be that OT was kind of its own isolated world
Right.
built around proprietary devices, often with security as an afterthought, not a primary design consideration.
Absolutely. But then things started to shift. These critical systems increasingly adopted standard networking protocols, your Ethernets, IPs, TCPs, UDPs, to handle control and automation. This obviously offers more flexibility and connectivity, but it also opens up a whole new can of worms when it comes to cybersecurity.
Yeah, it's almost like they become more vulnerable by becoming more connected. One of the key takeaways that really stood out to me from the material was this idea that you can't protect what you don't know you have. So before even thinking about security measures, you absolutely need a comprehensive and accurate inventory of every single asset in your ICS environment.
Absolutely. A solid asset management program is non-negotiable. Without it, you're essentially flying blind. Once you have a clear picture of your assets, the next step is understanding how they fit together. The material you provided goes into the typical hardware architecture of an ICS environment, and often you'll find an industrial demilitarized zone, or IDMZ, along with distinct components for control and automation.
Right.
We often talk about different security zones within an industrial network. You have the enterprise zone, which is your typical corporate IT setup. Then there's the industrial zone, where your most critical OT systems live. And sitting between these two, acting as a controlled boundary, is the IDMZ. Sometimes it's referred to as level 3.5 in some models, but regardless of the name, it's a critical element in your security architecture.
Okay, so let's unpack this IDMZ a little bit. The material describes it as a layer for sharing information between IT and OT. But instead of allowing direct communication, it relies on these broker services within the IDMZ to relay information back and forth. What's the advantage of this setup?
Well, think of it as adding an extra layer of separation, a buffer zone. It prevents those direct connections, which significantly shrinks your attack surface. So if something in the IT environment gets compromised, the impact on your sensitive control systems is greatly reduced. And get this, if a system within the IDMZ or even in the IT network above it gets compromised, you can actually shut down the entire IDMZ. This helps contain the breach and buy you valuable time to investigate and remediate while still allowing production to continue. So it's not just a network segment, it's a strategic choke point for controlling the flow of risk between your corporate world and your operational systems.
I like that analogy, a choke point for risk. So in terms of the presence of IDMZ assets within the enterprise zone, what does that typically look like?
It's usually kept to a bare minimum. You might see specific endpoint clients, things like web browsers or remote desktop clients, that allow authorized personnel to interact with the industrial environment through the IDMZ, but that's about it.
But surely there are cases where you need some level of connection back into the enterprise from the industrial side.
Absolutely. Certain applications, like systems that replicate historical process data for analysis or solutions enabling secure remote access for vendors, might need a limited presence on the enterprise network. Things like synchronizing databases or providing controlled entry points for remote experts through secure jump boxes. Then there are manufacturing execution systems, or MES, which often have components on both sides that need to talk to each other.
And the IDMZ itself, what are the core technologies that make it tick?
Network switches are the foundation here. The material specifically mentions robust managed switches that can handle VLANs, virtual local area networks, and redundancy. Cisco's 3850 series is highlighted as a good example, but obviously similar high-end switches from other vendors would also be suitable. These switches connect your virtualization servers within the IDMZ to the IDMZ firewall. They also allow you to logically separate the different virtual servers using those VLANs, kind of like creating virtual fences within the hardware.
So virtualization plays a big role in the IDMZ setup.
It does. The virtualization platforms within the IDMZ house those essential broker services we talked about. From a security standpoint, it's crucial to treat these virtualized systems as if they're part of the industrial zone itself. That means no direct internet access and typically manual updates to prevent any unintended modifications.
And you mentioned remote access using RDP as a common broker service.
Mhm.
How do you manage that securely through the IDMZ?
One common and secure approach involves setting up an RDP gateway server within the IDMZ. Then you configure your firewall rules to control access very tightly. For example, you might only allow connections from specific enterprise IPs to the RDP gateway over SSL, which is Secure Sockets Layer, a standard protocol for encrypting internet traffic. This would typically happen on port 443. Then, you would allow the RDP gateway to connect to specific industrial IPs using the standard RDP port 3389, as well as enabling communication with the industrial domain controller for user authentication.
Makes sense. What about controlling the traffic that originates from within the industrial network and needs to go out to the internet?
That's where forward proxy servers within the IDMZ come in. Tools like Squid, often running on a Linux server like CentOS, can be used to enforce both device and URL filtering for any traffic coming from the industrial network that's headed for the internet.
It sounds like modern ICS architectures really bake in a lot of security considerations from the get-go. The material you shared also talked about how industrial networks used to be structured, right?
Yeah, in the past, IT and OT were pretty much separate entities, physically isolated. From a pure cybersecurity standpoint, that separation was actually quite beneficial, but it led to a lot of different, often proprietary technologies, which made things complex. Managing spare parts and needing specialized expertise for each vendor's equipment was a real headache.
So this move towards IT-OT convergence is really shaking things up.
Exactly. Modern architectures are all about segmentation and even microsegmentation. The idea is to group related ICS equipment into dedicated subnets for their specific functional areas. These are often called security enclaves. Then you have a dedicated OT firewall controlling all communication between these enclaves and what's often referred to as level 3, or site operations. This level 3 acts as a kind of intermediary for any communication to or from the lower level ICS devices.
Right.
It prevents those uncontrolled direct connections and enforces clear security boundaries.
Understanding this architecture really lays the groundwork for how you actually go about monitoring the security of these systems. What are the main goals when it comes to security monitoring in an ICS environment?
Well, fundamentally, it's all about detecting any events that could have undesirable consequences for the industrial process. Things like the execution of malicious code or any unauthorized changes to the programs running on PLCs or HMIs, human-machine interfaces.
And what are the main approaches to security monitoring that are used in this context?
The material outlines three primary approaches: passive security monitoring, active security monitoring, and threat hunting.
Okay, let's start with passive security monitoring. The name suggests it's a non-intrusive approach.
Yeah, exactly. It involves collecting network data without actively probing those industrial systems or adding extra traffic to the network. Think of it like listening in on conversations that are already happening.
Got it.
The primary way this is done is by capturing network traffic using network taps, which are basically physical splitters in the network cable,
Okay.
and span ports, which are configuration options on network switches that mirror traffic to a monitoring port. This passive approach is usually preferred for ICS because it minimizes any risk of disrupting those often resource-constrained industrial devices. They're not always built with powerful processors and tons of memory. A common tool for analyzing this captured network data is Wireshark.
Okay, so passive is about observing without interfering.
Hmm.
What about active security monitoring? How does that differ?
Well, active monitoring takes a more proactive approach. You're actively sending probes and requests to systems on the network. One common example is vulnerability scanning. This involves sending specific requests to identify the services running on a device and their versions. Then you can compare this information against databases of known vulnerabilities to see if any of your systems are exposed. Nmap is a key tool here, especially when used with its service version detection flag, which is typically written as -SV.
So you're intentionally reaching out and poking those systems to understand their configuration and identify potential weaknesses.
Exactly. And there are also some active monitoring tools that are particularly relevant in ICS environments, like Modbus CLI, which lets you interact with devices using the Modbus Industrial Communication Protocol, and Pylogix, which lets you talk to Allen Bradley PLCs, which are very common in industrial settings.
Now, you also mentioned threat hunting as a type of security monitoring.
Yeah.
How does that fit into the overall strategy?
Threat hunting is more proactive and investigative. It's not just reacting to alerts that are automatically generated. Threat hunters actively dig through the network and system data, looking for those subtle signs of malicious activity that might not have set off any alarm bells. Think of it like a digital detective searching for clues.
I like that. So for passive security monitoring, what are some of the most common tools? The Imperial listed a few.
Suricata is a really powerful open source intrusion detection system, or IDS, that's known for its efficiency. It uses multi-threading, which can give you better performance on modern hardware with multiple cores compared to some older IDS solutions like Snort. Then there's Security Onion, which is a really comprehensive platform. It's open source and bundles together several key security tools. You've got full packet capture, intrusion detection with Suricata, network event analysis with Zeek, and host-based intrusion detection with Wazoo. It's basically an all-in-one security powerhouse. There's also Silent Defense and Lantopolog, which are great for network mapping, helping you visualize your ICS network layout.
And for active monitoring, besides the essential Nmap, what other tools are commonly used?
Nikto is a great tool for scanning web servers for vulnerabilities. It's useful for finding weaknesses in any web-based interfaces that might be part of an ICS. Then there's Nessus, which is a more comprehensive commercial vulnerability scanner that offers a really wide range of checks. And as we already discussed, Modbus CLI and Pylogix are essential for interacting with and testing the security of those specific industrial control protocols and devices.
With all the data generated by security monitoring in these complex environments, how do you make sense of it all? You mentioned the importance of threat intelligence earlier.
Right. Threat intelligence is vital. It's about gathering information from various sources to understand the threats that are actually relevant to your specific environment. This includes internal data, like logs of past incidents and vendor reports, as well as external sources like threat feeds. You can even set up honeypots, which are decoy systems designed to attract attackers within your network to get a first-hand look at their tactics and tools.
So you're using a combination of your own internal knowledge and insights from external sources to paint a clearer picture of the threats you face.
Exactly. And external threat feeds, which often include what we call indicators of compromise, or IOCs, things like known bad IP addresses, malicious domains, or file hashes from sources like Alien Vault OTX can be integrated into your CM systems. CM stands for Security Information and Event Management. These threat feeds help your CM detect known malicious activity more effectively. The material specifically mentions integrating them into a platform like Security Onion. While threat feeds aren't a complete threat intelligence program by themselves, they do add a valuable layer of defense.
You also mentioned endpoint monitoring as being crucial in ICS. How do you go about gaining that visibility into the security status of individual machines?
Wazoo is a great tool for this. It's a host-based intrusion detection system, or HIDS, agent that can be installed on your computers and servers to monitor their security posture. It works alongside your SIEM to give you a more comprehensive view of security events across your entire environment. And you can even enhance Wazoo's capabilities by using tools like Sysmin, which gives you really detailed process monitoring.
Okay.
And there's PowerShell script block logging on Windows, which tracks commands executed through PowerShell, which can be a common attack vector.
What about situations where installing agents on every device isn't feasible? I imagine that's often the case with specialized industrial equipment.
That's where syslog event log forwarding comes in handy. Lots of network devices and automation equipment in ICS environments can send their system logs to a central log collection point using the standard syslog protocol. Security Onion is one example of a platform that can receive these logs. The material even mentions forwarding logs from Silent Defense to a central analysis platform.
So you're pulling in data from various sources across your ICS. How do you then turn all that raw data into something actionable?
That's where SIEM solutions become really powerful. Tools like the ELK stack, which stands for Elasticsearch, Logstash, and Kibana, are designed for exactly this purpose. The ELK stack is also a core part of Security Onion, by the way. These SIEM solutions centralize and analyze security data from all those different sources, allowing you to visualize trends, correlate events, and set up alerts for suspicious activity. For example, you could create custom dashboards in Kibana to monitor your firewall for unusual patterns, or to look for specific PowerShell commands that might indicate an attack.
That sounds like a very comprehensive approach. But what about proactively searching for threats that might be hiding in your systems, even if they haven't triggered any alerts yet?
That's where threat hunting comes in. Remember, it's all about actively seeking out those hidden indicators of compromise that might have slipped past your automated defenses. For instance, you might have a hypothesis that there's malware lurking in your network that's periodically beaconing out to a command and control server. Tools like RITA, which analyzes Zeek network logs for this kind of beaconing behavior, and the volatility framework for memory forensics become really valuable here. Memory forensics involves analyzing snapshots of a computer's RAM to look for traces of malicious processes or code libraries. You can even reverse engineer malware samples using tools like IDEA Pro and OllyD to understand how they work.
Wow.
And there are tools like Yare that lets you create rules for pattern-based malware detection. You can scan your systems for those patterns, and CrowdResponse can remotely collect digital artifacts from your systems and perform Yara scanning across multiple endpoints.
It really is like being a digital detective. The material also mentions simulating command and control servers as a way to proactively analyze malware behavior. Can you explain how that works?
Sure, tools like iNetSim allow you to create a controlled lab environment that mimics common internet services. This is a safe way to analyze how malware samples behave when they try to connect to the internet. You can observe what data they try to send, what command and control servers they reach out to, all without risking your actual production network.
That's pretty clever.
Yeah.
And what about this idea of comparing system snapshots? It sounds like a useful technique.
It is. By taking a baseline snapshot of a system when you know it's clean, using tools like msinfo32 on Windows, you can compare it against a later snapshot to see what's changed. This can reveal new processes, services, or applications that might be suspicious. And of course, you always want to leverage those threat intelligence feeds we talked about to actively search for any known malicious indicators within your environment.
That makes sense. Attackers often try to move laterally within a network once they've gained an initial foothold. The material you provided specifically addresses this issue of suspicious external connections. How does this tie into ICS security?
Well, attackers often gain their initial access through the enterprise IT environment, which is often less hardened than the industrial side. Maybe they trick an employee with a phishing email, for example.
Right.
Once they're inside the IT network, they try to pivot into the more critical and often less closely monitored industrial network. So keeping a close eye on enterprise network logs for any unusual activity, like unexpected outbound RDP connections, can be a really valuable early warning sign. Another thing to watch out for is the risk posed by cached credentials, which can allow an attacker to move between systems very easily once they compromise a single account.
That's a good point. So to really gauge the effectiveness of your security and find areas for improvement, you need to conduct thorough assessments. What are the different types of cybersecurity assessments that are relevant for ICS environments?
The material outlines several key types: risk assessments, red team exercises, blue team exercises, and penetration testing.
Okay, let's take a closer look at each of these.
Yeah.
What's involved in a typical risk assessment for an ICS environment?
A risk assessment is all about systematically identifying and evaluating the security risks to your industrial control systems. There are several key steps. First, you identify all your critical assets. Then you identify the potential threats that could target them. Next, you assess the vulnerabilities in your systems. Then you analyze the potential impact and likelihood of those threats exploiting those vulnerabilities, and you calculate the overall risk level for each scenario. Finally, you develop mitigation plans to address those risks.
It sounds pretty comprehensive.
Yeah.
And how do red team and blue team exercises differ?
Red team exercises are essentially mock cyber attacks. You have a team of security professionals who try to breach your defenses, exploit vulnerabilities, and achieve specific objectives. They mimic real-world attackers. The goal is to test your security controls and find any weaknesses. Blue teams, on the other hand, are the internal defenders. In a blue team exercise, they practice their detection, response, and recovery skills as they try to thwart the red team's attacks.
So, red team is offense and blue team is defense.
Exactly. Penetration testing, on the other hand, is typically a more focused engagement with a very specific goal in mind, like trying to gain access to a particular system or modifying a specific control process. Penetration tests are usually time-boxed and have a clearly defined scope.
We've talked a lot about network and system security, but the material you shared also dives deep into the vulnerabilities that can exist within PLC code itself. That seems like a particularly critical and perhaps less well-known aspect of ICS cybersecurity.
Absolutely. As cyber attacks against industrial systems become more frequent and more sophisticated, the PLCs themselves, those workhorses of industrial automation, are becoming prime targets. And vulnerabilities in that PLC code can be exploited in all sorts of ways to cause disruption, damage, or even safety hazards.
What kinds of attacks can target PLC code specifically? The material lists quite a few, and some of them are, frankly, pretty concerning.
The list is extensive, and it really underscores the wide range of ways PLC code can be manipulated. You've got things like logic bombs, which are pieces of malicious code that sit dormant until a certain trigger condition is met, at which point they activate, potentially causing chaos.
Yeah.
Backdoors can be introduced into the code to provide unauthorized access. Attackers can inject entirely new malicious code to directly manipulate processes or steal data. They can subtly modify existing code to sabotage operations or tamper with data.
Wow.
Even deleting critical safety interlocks or operational logic can have devastating consequences. And attackers can manipulate or suppress fault messages, so problems go unnoticed. They can disable output signals, preventing control commands from reaching physical devices. They can duplicate instructions, which can lead to unexpected behavior or cause the PLC to run out of resources. And they can even exploit unused data tags within the PLC program as entry points for their attacks. Missing code elements like coils or instructions can also lead to unintended operations. And perhaps most importantly, a compromised PLC can be used to attack other devices on the same network.
That's a pretty sobering list of potential consequences. The material also mentions vulnerabilities that can impact HMIs and data transfer units, or DTUs.
Right. As HMIs and DTUs become more interconnected, they often rely on standard operating systems for additional functionality and remote access. Unfortunately, this means they inherit the same security vulnerabilities that are common in those operating systems. You also have vulnerabilities related to network segmentation. If the isolation between different parts of the network isn't properly implemented and monitored, attackers can jump between segments.
Okay.
And securing older PLC systems presents unique challenges because of limited resources, backward compatibility requirements, and the potential for performance impacts if you add security measures like IPsec encryption. These measures can sometimes introduce delays into the PLC's scan cycle, which can disrupt real-time control.
So with all these potential attack vectors targeting PLC code, what are some of the key strategies for detecting and preventing them?
Monitoring the PLC scan time for any anomalies is crucial. A sudden change in the scan time could indicate that malicious code has been added or removed. The material really stresses the importance of proper PLC alarm code design. Make sure alarm code is in dedicated routines, that alarms latch until acknowledged, and that all alarm events are logged. Basic security hygiene, like not using default passwords on your PLCs, is essential.
Right.
But it's worth noting that PLCs often don't have the same robust defenses against password cracking that you find in other systems. The Stuxnet attack was a real-world wake-up call. It showed just how sophisticated these attacks can be, targeting PLC software, engineering workstations, and HMIs.
Right. So this scan time monitoring seems like a really subtle but potentially important indicator. How might attackers intentionally try to manipulate the scan time?
Well, they can insert code that creates extra processing overhead, like those unnecessary loops we talked about earlier. This slows down the PLC. On the flip side, they could delete legitimate code to speed up the scan time, potentially disabling important checks. They can even manipulate a setting called the System Overhead Time Slice, or SOTS, which controls how the PLC allocates processing time between communication and control tasks. This can disrupt normal operation or even be used to hide malicious activity.
Oh, wow.
And another thing attackers can do is directly force the status of physical inputs and outputs, creating dangerous conditions that the normal control logic might not even detect.
Okay, so given all of these potential threats, what are some of the best practices for ensuring PLC cybersecurity?
Regular and thorough risk assessments, specifically for your industrial control systems, are absolutely essential. You need to understand your vulnerabilities. Targeted cybersecurity awareness training for all ICS personnel, emphasizing things like strong passwords and phishing awareness, is crucial. Keep all software and firmware up to date. Don't use default usernames and passwords. Regularly back up PLC logic and configuration files so you can recover quickly from a ransomware attack or other incidents. And finally, implement network segmentation to isolate those critical systems from less trusted networks.
Okay, well, we've certainly covered a lot of ground today. We've seen just how important a layered and comprehensive security strategy is for protecting these vital systems. From understanding the network architecture with that crucial IDMZ, to using both passive and active monitoring techniques, to leveraging threat intelligence, and even diving into those very specific PLC code vulnerabilities and how to mitigate them. This ITOT convergence presents both amazing opportunities and some serious challenges. A robust security posture is absolutely essential. I really hope this deep dive has provided some valuable insights and a clearer understanding of this complex landscape. But it also raises a crucial question. Considering the specific constraints and the critical nature of your own environment, what is the one area of ICS cybersecurity that you need to investigate further right now? Hello, Tech Unplugged podcast, and thank you for listening.